hello everyone. Am I audible? Am I audible?
Yes, you are audible.
Okay, thank you. Okay, so let's start. So the number of participant is decreased exponentially. So whatever, let's start. Okay, so let me share my screen. Yeah. So you can see my screen, right?
Screen is visible.
Okay, thank you. So let's start. First, we will do practice assignments of week 2 and week 3, and then we will do some other things. So let's see the questions of practice assignments. Okay, so here is a question I am writing here. So the question is, determine true or false right? So we have to determine the statement is true or false. So given that ring homomorphism phi mapping qx to q how we are defining this, fx is goes to f of 2. Any polynomial fx belongs to qx goes to phi of fx. Okay, so I denote this phi by this notation, this f of 2 for all fx in qx. Okay, fx in qx, then we have to determine the kernel of phi consists of all polynomials which are divisible by x minus 2. Then kernel phi is equals to fx belongs to qx such that x minus 2 divides fx. We have to say this statement is true or false. Okay, so tell me, is this true or false? How we will proceed? Okay, tell me. Someone want to respond? Some response?
Start with the definition of kernel phi.
Okay.
Kernel phi equal to.
Okay, kernel phi is equals to fx belongs to qx
such that f
phi
of
of
2
f,
is 0.
yeah,
Phi
such
of
that
2.
yeah, yeah, f of 2 is 0. Phi of fx is 0, that means f of 2 is 0. Okay, then
f of 2 equal to 0.
yeah. So what?
So set of all fx such that x minus 2 is a factor of f of x.
Yeah. So how you will claim that x minus 2 is a factor of fx, any fx in kernel phi? Then how you will say x minus 2 is its factor?
2 is a root.
Yeah, 2 is a root, right? So what?
So x minus 2 is a factor.
Yeah. So that's why fx x minus 2 divides fx, right? So I hope it is clear. Should I need to write? Okay, let me write. F of 2 is equals to 0. This implies fx belongs to qx such that fx is equals to x minus 2 times gx for some gx belongs to qx. this means x minus 2 divides x. So this statement is true. So the next question of the assignment, the practice assignment is okay. Second question. Let Z denote the ring of integer. Determine which of the following are ideals in the polynomial ring ZX. Okay. So given ring R is equals to polynomial ring with integer coefficients, and the set of all polynomials whose constant term is the, so we have to determine which of the following are ideals in the polynomial ring. Which of the following are ideals in R? So first statement is that the set of all polynomials whose constant term is equals to 0. The set of all polynomials whose constant term is equals to 0. Set of all polynomials whose constant term is equal to 0. Okay. So tell me, is this ideal or not? Okay. Response.
This is an ideal.
Okay. How you will argue?
0 is the root of all such polynomials.
Right. Right. So by similar, like we first did define this map like fx goes to f2. Now here replace q by z and 2 by x minus 2 by just x. Then you can just see this is the same. This is the map. Okay. You can just check that this, if you define this phi by like phi mapping zx to z such that phi of fx goes to f0, then you can see the kernel phi is precisely the polynomial fx such that x divides fx, and then you can see that this is an ideal. So this one is a true statement.
We want to find kernel.
Yeah, you can do in this way, right? Means if you define phi in this way, like here you define for evaluation at 2, if you define evaluation at 0, right, this phi map is just a evaluation at 2, right? Agreed or not?
We
So
want to
basically
prove,
yeah,
we want to prove it is an ideal.
yeah, kernel will be always ideal, right?
For
Do
that,
you know this
why
fact?
we have to find kernel phi?
Okay, let me write what I am saying. Okay, I hope you are missing something. Phi mapping zx to z, fx goes to f0. Matlab phi of fx equals to f0. I am defining the morphism in this way. Then you can see that kernel phi is precisely this one. Set of all polynomial whose constant term is equal to 0. Can you see now or not? Fx belongs to zx such that phi of fx is equals to, which is f0 is equals to 0. So now can you see this is same as the set of all polynomial whose constant term is equal to 0. If constant term is non-zero, then f0 cannot be 0, right? It will be some a0.
So kernel phi is an ideal, therefore you conclude.
Yeah, this is same as the, okay. Okay, suppose fx, the polynomial fx will be of the form a0 plus a1 x plus so on a n x to the power n. Then what is f0? F0 is a naught, but we are the element in kernel will be f0 should be 0. That means a naught should be 0. So that means this polynomial you can write as x times some gx, right? Just common out x, and then you would write that a1 plus a2 x plus a3 x plus an x to the power n minus 1. This is my gx. Now you can see precisely that this thing is the kernel phi is same as, so this is fx belongs to zx such that x divides fx, and you see about this same thing here. Here x is replaced by x minus 2, and you saw that this is there, this is the ID. So that's why this is the ID. Kernel phi is the ID. So this is the fact, right? Agreed or not? Can you see now or not?
Yes,
Yeah.
you say kernel phi is an ideal, therefore the given
Yeah.
set is an ideal.
Yeah, correct. Okay. The second part, the set of all polynomial whose constant term is equal to 1. So tell me, is this ideal or not? Okay.
This is not an ideal.
Why?
If you take two polynomials with constant term 1,
Yeah.
the sum of those two polynomials will have constant term 2.
Okay. So this is not the element. So
Closure
for
property.
yeah, so for ideal it should be additive subgroup. Is there additive identity in I?
Additive identity. Okay. 0 is not there.
Yeah. So that's why that is also a point, right?
Okay.
Yeah. So this is false statement. Third one, the set of all polynomial whose constant term is divisible by 3. Okay, tell me. Is this ideal or not? We are saying this I is equals
This
to,
is an ideal.
okay, fx belongs to zx such that 3 divides fx. Okay, sorry, 3 divides a naught. Okay, let me eraser. Oh. Okay. 3 divides where is this? Yeah. Oh. 3 divides this one a norm, where fx is equals to a naught plus a1x plus so on a n x to the power n. Oh shit. Yeah, this thing. Okay, so now we have to say this is the idea. So how we will argue? Response.
Take two such polynomials and find their difference.
Okay. Fx and gx. Okay. Fx is equals to this one, and gx, suppose gx is equals to same polynomial with coefficient b naught. Right? That b naught plus b1x plus so on bm x to the power m. That and 3 divides b naught. Right. So these two are in this set. So now you want to difference of these two. So fx minus gx will be a naught minus b naught plus a1 minus b1 x plus so on. You can get it. Okay. Now we want to show that 3 divides a naught minus b naught, right? How you will show?
3 divides a naught and 3 divides b naught implies 3 divides a naught minus b naught.
B naught, right? So 3 divides a naught minus 3 divides a naught and 3 divides b naught implies 3 divides a naught minus b naught. So that's why. So now there is also another condition, because you have to check this is ideal. So you check this is additive sum. So how you will check this is ideal?
If 3 divides a naught, then 3 divides any multiple of a naught, integer
Yes.
multiple of a naught.
Correct. So you choose any polynomial, gx belongs to zx. Now you are gx is in zx and fx is this polynomial in I, and fx belongs to I. You have to show, we have to show that fx dot gx is in I, right? So how we will show? Since like fx belongs to I, this implies that 3 divides a naught, and this polynomial gx, suppose gx is of the form c naught plus c1 x plus so on cm x to the power n. Now see how you multiply this fx dot gx. We just want to deal with constant term, so let me write only constant term. Constant term of fx dot gx is, what is the constant term? A naught c
C
naught.
naught.
A naught c naught. So now since 3 divides a naught, this implies 3 divides a naught c naught. This implies fx dot gx belongs to I. So this is an ideal. So this statement is true, right? True. So we have one last option remaining for this one. Okay, D. So what is D? It is saying the set of all polynomials such that the sum of all coefficient is 0. Set of all polynomials such that the sum of all coefficient is 0. So it is fx belongs to zx such that fx is equals to a naught plus an x to the power n, and a naught plus an is 0. Is this ideal? Tell me.
Not an ideal. You can take two polynomials with
Okay.
sum of the coefficient 0, but when you add or subtract, the condition may not be true.
Okay, give me such an example.
1 minus x.
Fx is equals to 1 minus x.
G of x also you can take g of x. F of this sum of the coefficient 0. Then 2 minus 2x.
Then it will be 0, right?
One minus x when sum is 0. You take just x only, will not consider x.
No, it is correct. Here it will be not fair, right? Fx minus gx is of the form a naught minus b naught plus a1 minus b1 plus, okay, plus so on. Suppose n is less than m, right? Suppose n is less than m. So an minus bn plus, sorry, now minus b n plus 1 so on minus b, right? Now you can rearrange this one, a naught plus a1 plus an minus b naught plus b1 plus bm, this one, correct? So this one is 0, this one also 0, right? That means this is 0. Sum of all coefficient is 0. Coefficients, sum of coefficient of f, right? Agreed or not? Please respond.
So this is also an ideal, right?
So till now we cannot say, we just check that it is additive subgroup. Zero
When sum
element
is 0, any multiple. Okay.
Tell me.
Yes, sir.
We can try with some example in which the condition is not true.
Why you want to that, or why you want to always do counter? Let's do for a proof. If we stuck, then we will do for counter example.
Okay.
Because basically I always do this approach. First I will go for a proof. If this is stuck, then I will go for a counter example. So tell me if you are finding any counter example, so let me know. Otherwise I will go for a proof, and if I stuck, then I will go for counter example.
Sir, one counter exam, sir.
Yeah,
Sir,
give me.
f of x equal to 1 minus x,
Uh,
and then g of x is equal to 3 minus 2x minus x square.
3x minus
3 minus constant term 3 minus 2x minus x square.
Yeah.
So f of x minus g of x is
F of x minus g of x is equals to 1 minus 3 minus 2 minus x plus 2x plus x plus x square, right? So this is right. This is holding, right?
Is not false. Still.
Yeah, we give proof for this, right? So here you cannot get counter example. You can get counter example on multiplication only, if possible.
Now you find out the product of these two polynomials.
Okay. Fx dot gx is equals to 1 minus x dot 3 minus 2x minus x square. So this is 3 minus 2x minus x square minus 3x plus 6x square plus x cube. So let's rearrange this in a good way. 3 minus 5x plus 5x square plus x cube. So minus 5 plus 5 and 0, 3. Okay, so this is, here it is failing, right? This one is the counter example. So that's why this
3
statement
minus 2x minus x squared minus 3x plus 2x squared. Multiplication is wrong.
Okay. So let me check. 3 minus 2x minus x square minus 3x plus 6x square.
2x squared.
Oh, sorry. 2x square. Sorry. plus x cube. Oh, sorry. So 3 minus 2x minus 3x 5x plus x square. So 2x square minus x square x square.
Yeah.
Right? So now it is minus 5. So the sum of coefficient is what? Sum of coefficient is equals to 3 minus 5 plus 1 plus 1. Plus 1. So what is this? Minus 2 plus 2, it is 0, right? So it is 0. It is not giving counter example. So let's go for a proof because it is sticking. So if you have any other counter example in mind, you can give. Otherwise, I will go for a proof. Muthu Kumar, do you have any idea? Okay. If not, then go for a proof. If we will stuck, then we will again come for counter example. So suppose fx belongs to I. This means a naught plus so on an is 0. And we take any element gx in zx. Gx is equals to p naught plus p1 x plus so on bm x to the power n belongs to zx. We have to show fx dot gx in I, right? So what is fx dot gx? E naught b naught plus E naught b1 plus E1 b naught x plus okay E naught b2 plus E1 b1 plus E2 b naught x square plus so on En bm x to the power n plus m. Now we want to show that E naught b naught plus E naught b1 plus E1 b naught plus E naught b2 plus E1 b1 plus E2 b naught plus so on n bn is equals to 0. We have to show this one. This does not seem to me that this should be true, but yeah, let's see. So what you can do, we just want to break out every term, take b naught common, then can we do something everywhere b naught term e naught? Yeah, we can do something, right? I feel that.
Excuse me,
Yeah, tell me.
we want to find only sum of the coefficients.
Yeah,
So now, when you multiply fx into gx, a
Yeah.
naught into b naught plus b1 plus etc. bm.
yeah,
So that is one sum. Then a1 into b naught plus b1 plus
yeah, you are
etc.
saying correct. Yeah, means like, but you have to say in opposite direction. Just multiply b naught to this one, and this one is already 0. Similarly, b1 to this one, but this one is already 0. So you are done, right? You are arguing in this. Correct or not? I hope you are saying this. Let me write. You are saying in this way, but that's nice way. Your observation is good. So write in this way. B naught and this like multiply B naught first with this polynomial. What is the polynomial? Whatever the polynomial fx plus b1 x dot fx plus so on bm x to the power m dot fx. So now see, we just want to sum of coefficient. So this is here the sum of coefficient is a naught plus so on plus a n. Here the sum of coefficient is b1 dot a naught plus so on a n. Similarly here the sum of coefficient is bm a naught plus so on a n. But you can see this one is already 0. This one is already 0. Yeah, so all are 0. So this means sum of coefficient is 0. So the statement is true. So you all are trying for counter example, the statement is true. So this is the true statement, right? Agreed or not? True statement. Any doubt? Any doubt? Can I go for next question? Please respond. Otherwise, I will be bored for this 2-hour discussion.
Please proceed.
Yeah, okay. Thank you. So now third question. Select all true statements. What I am writing. Okay. You all know definition of ring homomorphism, right? Should I need to write definition of ring homomorphism? This is the problem, is no one want to respond.
Sir, one time recall.
Yeah. Okay. Should I need to recall?
Yes, sir.
Okay. So you know all know definition of a ring. Suppose R1 and R2 are two ring. Then phi is a ring homomorphism from R1 to R2 if phi of A plus B is phi A plus phi B. This is the first condition. The second condition is that phi of AB should be phi of A dot phi of B. The third condition is that phi of 1 should be 1 of R1, you can write, should go to 1 of R2. Okay. So this is the definition of a ring homomorphism. It is a function from R1 to R2 such that it is additive and multiplicative and goes unit to unit. Unit goes to identity goes to identity. Okay. So let's go for this question. So first statement is that A, let R be any ring, there is a unique ring homomorphism from Z to R. Let R be any ring, then there is a unique ring homomorphism from Z to R. So okay, first give me a ring homomorphism from Z to R and then claim that it is a unique. Except this, no one and no other exists. So respond please now. Response, waiting for your response. At least give me one homomorphism, then I will try to show it is unique. Please give me. Okay. Why no one is talking? Let me check the names. How much?
Phi of 0 should go to 0 and phi of 1 should go to 1.
Yeah. So what? Suppose phi is a ring homomorphism. Phi mapping Z to R. So you are saying that phi of 1 should be 1, phi of 0 should be 0. Yeah, right. Then what? So phi of n, what?
Phi of n is 1 plus 1 plus 1 n times.
So if n is negative, then what?
So first you consider the case n is positive, then we'll go for n is negative.
Okay, case
Because
1. Yeah, okay. Case 1, if n
additive
greater,
inverse of 1 is available.
yeah. So if n greater than 0, phi of 1 plus, okay, then you can write is phi 1 plus phi 1. This is n times okay. So this is n times phi 1, and this is n basically. N times phi 1 goes to 1 of r. Okay, this one. Okay, so what about if n less than 0? So tell me now what I do.
Phi of -1.
Yeah, -1 plus -1 n times बराबर phi -1 plus so on plus phi -1 बराबर equals to n times phi of -1. But I want to show this is minus n dot 1 r. So you have to show this phi of -1 is matlab minus times phi of there is lack of space. So we have to, okay, we have to show. So tell me how you will show this. Tell me. Phi of -1 is minus times phi of. How we will show this?
Phi of 0 equal to phi of 1 minus 1.
Okay. This is 0.
Which is equal to pi of 1 plus pi of -1 plus
Phi of -1. Okay.
pi of -1. So that is
Okay.
one is the inverse of the other.
Yeah.
Additive
Yeah. That means
inverse.
phi of minus of phi of 1 is equals to phi of -1. Yeah. Correct. So this is the done. So you determine this homomorphism, right? So if there is a homomorphism, you just use the property and you show that if there is a homomorphism phi mapping Z to R, then you determine at all elements it has only one choice. So it is a unique ring homomorphism. So if phi is a Z to R and is a ring homomorphism, then one should go to one. Then you check that for all n in Z, the choice of phi n is fixed always. So there is so we have shown. So what I am writing is so we have shown that there is exactly one ring homomorphism from Z to R. Okay. 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 So now, okay, let's first do a similar question here. Then we will do part second option of this. Okay. From Q to Q, you have to determine question. Determine all ring homomorphism phi mapping Q to Q. So now we determine Z to R that there is a unique homomorphism. Now you have to show me for Q to Q there are how many ring homomorphism. Okay, so how we will proceed? Response. Okay, no one want to talk. So then I will erase this question and just do options. If you don't want to learn, just do options only. No one even responding. Nagmani, do you have any idea how we will proceed? We have to determine all homomorphism. Sai Ganga. Vibha Avasti. Okay. Okay. If no one want to respond, then just erase this question and do B part. If you okay. Okay, let's do B part. If no one want to do interesting questions, so let's do only on your practice assignment. There is a ring homomorphism from Z mod 3Z of integer modulo 3 to the ring Z mod 6Z of integer modulo 6. There is a ring homomorphism from the ring Z mod 3Z to Z mod 6Z. Okay, tell me, can there be a ring homomorphism from Z mod 3Z to Z mod 6Z? If yes, then give me. If no, then give me an argument why, or give me a proof why this is not true. Okay, no one wants to talk, so let me write. Suppose there is a ring homomorphism phi mapping Z mod 3Z to Z mod 6Z. Then what? It should take 1 to 1, 0 to 0, right?
Phi of x equal to 2x.
Phi of x equals to 2x. Then 1 will be not go to 1, right? But we want ring homomorphism such that 1 goes to 1. So phi of 1 should be 1 and phi of 0 should be 0. What is phi of 2? Phi of 2 is means phi of 2 means 2 bar, right? Here 2 bar. This is 1 bar plus 1 bar. This is phi of 1 bar plus phi of 1 bar. This is 1 bar. Here 1 bar means you come in Z mod 6Z. 2 bar. So claim phi is not a ring homomorphism. Claim phi is not a ring homomorphism. So how you will prove? Okay, now everything is in front of you. Tell me how you will claim that phi is not a ring homomorphism.
என்ன பாக்குறீங்களா? கரண்ட் இல்லையா என்னன்னு பாதி கரண்ட் போகும்.
Okay. Okay. No one want to respond. So let me write. Phi of 2 bar 2 bar is equals to 2 bar plus phi 2 bar plus phi 2 bar. But this is 2 bar in Z mod 6Z plus 2 bar. This is 4 bar. And this is phi 2 bar 2 plus 2 bar 4 bar. This is phi of 1 bar. So this is 1. But 1 does not equals to 4. Ring homomorphism. This implies there does not exist any ring homomorphism from Z mod 3Z So we proved that there does not exist any ring homomorphism from Z mod 3Z to Z mod 6Z. Now third part. There is a ring homomorphism from Z mod 5Z to Z mod 10Z. Sorry, there is a ring homomorphism from Z mod 6Z to Z mod 3Z. Now converse one. There. Okay. So tell me.
Identity.
If yes, then give me one. Yeah.
Identity mapping will serve the purpose.
What you mean by identity? Like, it is not clear in this case, right? Because
that is 1 bar going to 1 bar, 0 bar going to 0 bar, 2 bar going to 2 bar, 3 bar again going to 0 bar, because 3 bar in Z, 3Z is 0 bar.
two bar should be 2 bar, phi of 3 bar should be
Phi
0
of
bar,
3 bar
phi of
equal to 3 bar, which is 0.
so phi of
Phi
4
of 4
bar
bar equal
should
to
be
1
1.
bar.
Yeah. Sorry, I should write bar also. Phi of 5 bar should be 2 bar. Right. So how you will check this is a ring homomorphism? Now you have to check that phi of A plus B is equals to phi A plus phi B for all A comma B in Z mod 3Z. Phi of AB is equals to phi A dot phi B, and phi 1 is also 1. So you have to check this one, these two. But tell me, is there exist any other ring homomorphism except this from Z mod 6Z to Z mod 3Z? You can check this. It is easy. This is a ring homomorphism because you can just go by definition and can check it. Easy. These two conditions. So can you tell me, is there any other ring homomorphism from Z mod 6Z to Z mod 3Z? Just go by definition. Like I go in B part. Okay, let me suppose phi mapping Z mod 6Z to Z mod 3Z. If there is a ring homomorphism, then what? Phi of 1 should be always go to 1 by definition. Phi of 0 should go to 0. Now phi of 2, matlab 1 bar here, 1 bar here, 0 bar here, 0 bar. Phi of 2 bar should go to phi 1 bar plus phi 1 bar. This is 2 bar. Phi 3 bar should be phi 1 bar plus phi 1 bar plus phi 1 bar is equals to 1 bar plus 1 bar plus 1 bar, which is same as 3 bar, which is same as 0. So similarly, phi of 4 bar you can do by same construction. This is 1. Similarly, phi of 5 bar, this should be 2 bar. So this is the only possible choice of function. The choice which Muthukumar give is the only choice of function for ring homomorphism, and you can prove that this is a ring homomorphism. Only possible choice. Possible choice for ring homomorphism. So yeah. So what we have done? We have proved that there is a ring homomorphism from Z mod 6Z to Z mod 3Z, and even that ring homomorphism is unique, except that no other ring homomorphism from Z mod 6Z to Z mod 3Z. So now what? Next option. There is a ring homomorphism from Z mod 5Z to Z mod 10Z. Whatever, this is D part, I guess. There is a ring homomorphism from Z mod 5Z, Z mod 10Z. Tell me, is this true or false? Now you have idea that how we will proceed and how we will show if they exist or not. Now you can say something, right? Nagmani, whatever, Nagmani, I guess. You can respond.
This is not ring homomorphism, sir.
There is no ring homomorphism.
Yes, sir.
How you will proceed?
One second, sir.
Okay.
As in part B, you can do.
Yeah, similar to C part, right? So tell me, Nagmani, I am waiting for your response.
Yes, sir. I think. One second, sir.
Yeah. Okay. You are responding or not? Okay, fine. Okay, let me write. Suppose there is a ring homomorphism. There is a ring homomorphism. Then what? Phi mapping Z mod 5Z, Z mod 10Z. Then what? Then 1 should go to 1 bar, should go to 1 bar, 0 bar should go to 0 bar. Similar by same construction as I did above. 2 bar should go to 2 bar, 3 bar should go to 3 bar, 4 bar should go to 4 bar. Okay. So now you have to say that this is not a ring homomorphism. Now you can say This is not a ring homomorphism because like phi of 4 bar plus 4 bar, you can say this is phi 4 bar plus phi 4 bar. This is 4 bar plus 4 bar. This is 8 bar in Z mod 10. Right? But this is phi of 4 bar plus 4 bar is 8. 8 is 3, right? Phi of 3 bar, which is 3. But 3 does not is equals to 8 bar, does not is equals to 8 bar in Z mod 10Z. So you conclude that, so we conclude that there does not exist any ring homomorphism from Z mod 5Z to Z mod 10, right? So now next part. There is a ring homomorphism from Z mod 10Z to Z mod 5Z. Now tell me, this is true or false?
True, sir.
True. So give me argument. What is the your candidate for ring homomorphism? What is the function?
Identity.
Okay. So identity function. Right? So 0 bar goes to 0 bar. 1 bar should go to 1 bar. 2 bar should go to 2 bar. 3 bar should go to 3 bar. 4 bar should go to 4 bar. 5 bar should go to 0. 6 bar should go to 1 bar. 7 bar should go to 2 bar. 8 bar should go to 3 bar, and 9 bar should go to 8 bar. And you can check that it satisfies phi of a plus b is equals to phi a plus phi b. Phi of ab is equals to phi a dot phi b for all a comma b in Z mod 10Z. Okay. So this practice assignment is done. This is the second week practice assignment. Okay. So now we will do next practice assignment, which is of third week. So let me open that. Okay. Question 4. Question number 4. Determine true or false that R be ring, I be an ideal of R. Okay. R be a ring and I be an ideal of R. Suppose that I contains no zero divisor. Suppose that I contains no zero divisor. suppose that I contains no zero divisor, then we have to say then I is prime ideal, true or false? I is a prime ideal, true or false? So tell me, this is true or false? R be a ring and I be an ideal of R. Suppose that I contains no zero divisor. You know definition of zero divisor, right? Please respond. Muthu Kumar, do you know definition of zero divisor?
Zero divisors, two non-zero element product zero means those two non-zero elements are called zero
Zero.
divisors.
Right. Okay. So, so this statement is true or false?
It is. Then I is a prime ideal.
True or false?
Because you can take AB equal to 0 with A not equal to 0.
If there is no zero divisor.
I contain no zero divisors.
Yeah. Nagmani, this is true or false? What is your intuition?
I think false.
So give me counter example.
Counter example.
You can take zero ideal.
EZ6.
Sai Ganga, what's your idea? Please unmute yourself if you are in class. There are 4 to 5 participants. Everyone can unmute yourself. Vibha Avasti. Okay. So think in, suppose take R is a ring of integer, then there is a no zero divisor. So can you, is every ideal is prime ideal?
No, sir.
Yeah.
No.
Why? Give me a I gave you idea, right? You can think in ring of literature. What are the ideals which are not prime ideal? Because every ideal here is does not contain zero divisor, right? Because there is no zero divisor in ring of integer. So give me an ideal which is not a prime ideal in ring of integer. Why no one want to respond?
Take zero ideal.
Okay, then what?
Assume AB equal to 0 so that AB belongs to I.
Huh?
And assume A not equal to 0, therefore A is not in zero ideal.
Okay.
A not equal to 0.
Okay.
Right?
Yeah.
If we take B equal to no zero divisors means B must be equal to 0.
Huh?
A be 0, A not equal to 0 means B must be 0.
Yeah.
That is B belongs to zero ideal.
Yeah.
So that is AB belongs to that ideal means either A is in that one or B is in that one.
So you want to say zero ideal is not prime ideal in Z? You are claiming this one?
It is a prime ideal.
So what? So you are saying this statement true or false? What about 4z in ring of integer ideal 4z? Is this prime ideal? Two dot two equals to 4 belong to 4z, but 2 does not belong to 4z, right? Agreed or not? Nagmani?
Sir, one example, sir. Digit 8, sir.
Yeah.
Digit 8.
I could not hear you. Can you tell again?
Digit 8, sir.
Z8.
Z8. Z8. Z8.
8z means. Okay.
I1. So I equal to set for 0, 4.
I equals to
0, 4
0, 4.
is ideal but not prime ideal.
Okay, you are looking in ring of integers. Sorry, Z8 ring.
Is that
R
is
equals to- yeah. So you are saying that this is an ideal but not a prime.
but not a prime ideal, sir.
But is I contain 0 divisor? Yeah, it contains 0 divisor, right?
0
4,
divisor.
4 is a 0 divisor, right?
Yes, sir. 4 is a 0 divisor. But
I contains no 0 divisor. It should not contain 0 divisor, right? So this example does not. So why you are thinking for this? Think for ring of integer. I even tell you 4z. Take ideal I 4z. Is it a prime ideal or not? Does it contain any 0 divisor? Is ring of integer have any 0 divisor? Please respond. Is ring of integer any contain any 0 divisor? You don't even know this?
Z contains no 0 divisors.
So this is the question for you guys. Is ring of integers Z contain any 0 divisor? Any non-zero 0 divisor?
sir, another one example, sir. Z3. Z3.
First reply this one. Is ring of integer contain any non-zero 0 divisor?
Why this non-zero 0 divisors? 0 divisors are definitely non-zero.
Zero as a 0 divisor. So it's just so that's leave this thing. Don't write non-zero. Maybe like there are some convention like in your course they are teaching 5 1 go to 1. You take two integer non-zero integers, can their product be 0? Why you taking this much time? Take two non-zero integer, can their product be 0?
No.
Okay, so why you are taking this much time? No. So now tell me, now take any ideal in ring of integer which is not a prime ideal, because it by definition it will not contain any 0 divisor. So what are ideals in ring of integer which are not prime ideal? Because I want to disprove this statement. Okay. Take ideal I is equals to 4z. Then since z does not have any 0 divisor, this implies I does not have any 0 divisor. Now what? We have to claim.
It's me. 2 into 2, 4 equal to 0.
Yeah.
So 2 is a 0 divisor. How will you say I Does
2
not
into 2,
have
how 0
any-
in, you are in not in Z mod 4Z, you are in ideal 4Z. In ring of integer, ideal generated by 4. This contains precisely the element multiple of 4, like
Multiples
minus
of
4, minus 8, 0, 4, 8, 12, this one, so on, so on, so on. Then
Okay.
claim 4Z is not prime ideal. Ideal. 2.2 is equals to 4 belongs to 4Z, but 2 does not belong to 4Z, right? So this implies this statement, given statement is false statement. So this one is false statement, false. Give me some other example, ideal in ring of integers. This is not a prime ideal. Now I hope you have some.
Any composite number times Z.
Yeah, correct. Good observation. Because otherwise, if you take prime number, then it is always be like prime ideal, because you can see like if you take any prime number, then PZ ideal, then Z mod PZ is isomorphic to ZP, integer modulo P. So basically that is the field. So you can use that fact that if P is maximal, if and only if Z mod P is a Z mod P is a field. So that, yeah, R is a M is a maximal ideal in R, then if and only if R mod M is a prime ideal. Sorry, R mod M is a field. Okay. So choose all correct statement. Z denote the ring of integers. Question 5. Statements. Teachers. Okay. So what is the first option? N be positive integer, the quotient ring Z mod Nz is a field if and only if n is a prime number. Let n be positive integer, n greater than 0, n belongs to Z plus the quotient ring field if n only if n prime. True or false? Tell me.
It is true.
Okay. How? Suppose Z mod Nz is filled, then claim that Nz is a prime ideal. How you will claim?
You want to use maximal ideal. NZ is a maximal ideal if and only if n is the prime number.
Yeah, what you are saying? Tell me again.
NZ is a maximal ideal
M is a maximal ideal. So
if and only if n is the prime number.
okay. So how you will prove that?
So when NZ is a maximal ideal, Z by NZ is a field.
Okay. So how you will prove that? This is the same statement, right? Is
R
the
by
proof
I
done in
is a
class,
field.
or should I do? This proof, I guess, done in class, right? Or not? If not, I can do. If
R
done,
by
then
I is a field if and only if I is maximal.
That is correct statement, but have you done the proof of this? I hope you've done, right? I see on your notes it was done. So let me leave this one. This is correct statement. True statement. So B1. The number of units in Z mod 10Z is 4. Tell me, is this correct or not? Muthukumar, is this
So number of units is the number of integers which are relatively prime to 10 and
Okay.
less than 10.
number of units is equals to in Z mod NZ is equals to what you are saying? Number of integers
Less than 10 and relatively prime to 10. So that is
and less than 10. 1, 3,
7.
7, 9, right? These are the only one, right? So these are only 4 numbers. So this one is a correct statement, right? Number of units in Z mod 10Z is 4. So next option is there exists an integral domain containing 29 elements. Is this correct or not?
There exists
Domain. This is true or false?
Z by 29 Z.
Z by 29.
29 Z.
Why it will
Quotient.
be integral domain?
Because 29 is a prime number, therefore
no zero divisors.
the product of two non-zero elements never be 0.
Okay, right. So even it is a field, right?
Yes.
So this is a correct statement. Z is a subring of a ring R. Then R is an integral domain. Correct or not? Tell me. Muthukumar, tell me.
So this is
Nagmani, is this true or not?
True, sir.
True.
Yes.
Give me proof.
Z is no zero divisors.
Yeah. So what? In Z
No
there is a
zero
node zero
divis-
divisor. So how you will conclude that that ring R does not have also does not have any zero divisor?
Every non-zero divisors is called integral domain.
Okay, so I guess you are not understanding. Suppose Z, Z is a subring of R means there is an inclusion from Z to R, and now you are claiming Z does not have any zero divisor. You are claiming that R also does not have any zero divisor. But there can exist, there can exist X comma Y R such that X comma Y does not belongs to Z, but XY is equals to 0. This is possible choice, right?
So
There
you
can
have
be
to
zero divisor.
look for a counter example then.
Okay, so give me counter example. Tell me.
Q is a field.
Q is a field. Okay. So what?
So it is an integral domain and it has no zero divisors.
Yeah. So what?
Z is a subring of Q.
Yeah. But Q is an integral domain. So it does not disprove this statement, right? Think. Any idea? How you produce zero divisor nilpotent element by quotient of a polynomial? Do you have any idea? Like you can sit Z inside some polynomial ring ZX and then can do quotient to produce some zero divisor or nilpotent, right? So how you will do that? I guess you have some idea. Muthukumar, do you have any idea?
We have to look for some counter example.
Okay, so give me counter example. I gave you some idea. Look over polynomial ring of integer like ZX, do some quotient, and then give me like quotient to produce zero divisor. Okay, no one have some idea. So take R is equals to ZX mod X square. This one. Now tell me, is Z is a subring of this ring? Because Z2 ZX mod X square, there is an inclusion ring homomorphism, right? 1 goes to 1, 2 goes to 2, like because 2 is an element of ZX, 3 is an element of ZX, but quotienting X square just killing the ideal generated by X square, nothing else. So now you can see that X square is nilpotent. Sorry. X is nilpotent in ZX mod X square because X square equals to 0, but and Z is a subring of this one of ZX mod X square. This implies what? Given statement is false, right? Agreed or not? Hello. 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 Am I audible?
Audible, sir, but even slide is not visible, sir.
Cannot hear you. Let me write something in chat. Okay. Am I audible? I cannot hear you. I don't know what is the issue.
Hello.
Please respond in chat box.
Hello.
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 Hello. Hello.
Hello.
Audible. Cannot hear you. Please respond in chat box. I cannot hear you. Hello. Hello.
Hello, sir. Hello. Hello.
Hello. Hello. There is some issue. I cannot hear you. Let me leave and I will join again. So now can you hear me? Hello. Muthu Kumar, can you hear me?
I can hear you, but the screen is not visible.
Okay, I will share screen, but please respond because I thought you cannot hear me. Okay, so let me share. Okay. Wait a second. Wait a second. So Vidha Avasti, you are host. Please make me host because when I leave the meeting, you become host. Because other. Nagmani, please make me host. Oh.
Hello?
Yeah, please make me host. Otherwise, I could not share my screen.
Sir, your voice is audible, sir, but slide is not visible, sir.
Please make me host because you are host. Because when I leave the meeting, you become the host. So I could not.
How